Good evening, everybody.
Hola.
Got a few more people joining in here. So welcome to tonight. If you remember, last time we didn't quite finish last lecture, so we're going to wrap up the last lecture first, and then we're going to start up this lecture. But before we start either of those lectures, would anybody have any questions that they'd like to ask me? Is anything that they'd like to know about homework or anything else that we covered before? Any questions before we start? Okay, so then let's get started. There we are. Okay, so where we left off last time, we had talked about normal strains. We had talked about shear strains. Yeah, this last problem, example 3, was all about shear strains. And so now what I want to talk about is average normal strains. When a body distorts, we can also find the average normal strain along any path. So this is for like a solid body, as opposed to where we started it with normal strains were like cables and rods and things that were uniaxially loaded only. But we can apply this to more of a solid body as well. For instance, like this. So this is one of the problems where we found the shear strains by finding the change in the angles at each one of these corners. And the shear strain was defined as pi over 2 minus theta, that angle. But as this body distorts, as you can see, the distance from A to B changed. And the distance from C to D, this corner, that distance changed as well. So with a change of distance in a normal direction, we also have a normal strain, and we can calculate what that is as well. So in the previous example, we calculated the shear strains at each corner. We can also look at the average normal strains along lines AB or CD. From observation, we can see that the length of AB was reduced while CD was increased. So this one got stretched out longer, this one got compressed. Strain from each line can be found by dividing the difference in of the original length and the new length by the original length. Or epsilon, our symbol for strain, is our new length minus the original length over the original length. So if I take this example here, where we have some sort of a solid plate with these dimensions, then you can see that this thing did not distort evenly. This is 15 millimeters of distortion. This is 30 millimeters of distortion. So what is required is find an average normal strain along the lines AB and CD. Solution. So line AB, our original length, you can use Pythagorean theorem, where the horizontal is 150, the vertical is 250. So I just take the square root of the sum of the squares, and my original length was 291.548 millimeters along the diagonal. My new length, L, I do the exact same thing, but now the horizontal is the 150 plus the 30, so that's 180 over the 250. And my new L is 308.058. So therefore, my average strain along AB is the 308 minus the 291 over 291 is 0.05663 millimeters per millimeter. And it is positive. It did stretch out. You can see this line here is longer than the original, so this is in tension, as indicated by the positive. For line CD, I have the same original length, 150 over 2, or 150 squared plus 250 squared, take the square root, 291.548. But now the new length, I have the 150 minus 15. So now my horizontal is 135 and the vertical is still 250. So the new length is 281.121. So my strain is 284 minus 291 over 291. I get minus 0.02547 millimeters per millimeter. And that tells me it's in compression. So if this was, say, a steel plate, the steel is in compression in this direction. The steel is in tension in this direction. And so my final answers, and I box them, and that is it. Any questions about that last concept? Okay. So that was it. That didn't take very long to get caught up on that one. All right, so for tonight's lecture, we're going to talk about stress and strain components first. And this is going to help you directly with your homework that is due next Tuesday. So if we start with a 2-inch by 2-inch block, like so, and this block is defined 2 inches by 2 inches, and it has 600 pounds of tension on the block. Then to find the normal stress, we will use stress is equal to P over A. So the P is 600 pounds clearly, and the A is 2 by 2 is 4 inches squared. So my normal stress is 150 PSI. And to find the shear stress, we use tau is equal to V over A. I have no shear force on this block. So I have 0 pounds over 4. I have 0 PSI of shear stress, right? Simple. I've got 150 PSI of normal stress, 0 PSI of shear stress. These stresses are assumed to occur on a plane perpendicular to the long axis of the bar as shown. So if I take a cut right where the dotted line is, and excuse me, and I separate these pieces and create a free body diagram, then I have the 600-pound reaction on the left-hand side. I have my 150 PSI of stress on the interior. Remember, this is an interior cut, like so. And if we cut along the normal plane, we see that the normal stress is equal to 150 and the shear stress is equal to 0, as we said. So it would seem obvious that this loading creates normal stresses only. There are no shearing stresses. But is that true? Are there truly no shearing stresses? What if we look at a state of stresses on some other plane, say inclined at 40 degrees? So instead of taking a vertical cut through this thing, what if I take a slice at a 40-degree angle on this thing with the same bar, same 2-inch by 2-inch, and the same load, 600 pounds of tension? So looking at a free body diagram on a side view, I still have 600 pounds to the left. I have 600 pounds to the right, because by equilibrium, there are no other forces on this. It has to have 600 pounds of tension everywhere along this bar. So taking just a look at the left-hand side, free body diagram, I have 600 and 600. Seeing that the 600 pounds is not aligned with the cut plane, we can find the components that are normal and parallel to the cut plane. So I can my original 600-pound resultant, I can find the two components of that 600 pounds. I have a component that's in the shear direction, I have a component that's in the normal direction, and I have a 40-degree angle between the two. So remember, second lecture, I believe, we talked all about how to do vectors and combining vectors into a resultant. And we can also break a resultant into two components 90 degrees apart, aligned on any angle. Any angle is fair game. So we can certainly do this such that the addition of the shear and the normal brings you right back to the original horizontal 600-pound vector. Now we can use trigonometry to find our components. So the normal is going to be sine of 40 degrees of the 600 pounds. And if you kind of transpose the normal over here, this is your angle. So sine is opposite over hypotenuse. So that's how I got sine. And sine of 40 of 600 pounds is 385.7 pounds. The shear is the adjacent over hypotenuse. That's cosine. So cosine 40, 600 pounds is 459.6 pounds. Okay, does it make sense, everybody?
Yeah.
Okay, good. So now I have the two components of my original that are now aligned with the cut plane. One is parallel, one is perpendicular. So there is shear on this section, isn't there? We just said a minute ago there's no shear, but there really is shear. It's just on what direction that we have to look at that we get the shear. So if I recreate this, I have 459.6 pounds of shear, 385.7 pounds of normal force on this plane. Now, to find the stresses on this plane. But we have to remember that stress is equal to a force over area. What is the area of this cut plane? So the width of it is certainly the 2 inches. Okay, shouldn't the y component be negative? Which one are you saying is the y component, the normal or the shear?
The shear.
Okay. Not necessarily. I hadn't really considered that. In order for it to be negative, you have to have a sign convention. And I don't even really have an X or Y dimensions on here. It is in this direction, but is that negative or is that positive? Is only based upon your sign convention.
So if it's positive, shouldn't be the X like be negative? Because they look like X and Y. One of them should be negative. I don't know.
Okay. That's fine, but that's fine, and that's actually a good question. But you see the direction of my arrow? So as long as the arrow is in the right direction, then the scalar magnitude is positive, right? So I'm indicating the direction by the arrow, and this is positive. But that's a good point. If it was negative, is that negative shear? Hadn't really considered positive or negative on this. Suffice it for now, we don't really have a sign convention because I don't really have a coordinate axis system set up on this one. I just know that my 600 breaks down into these two components. Is that okay?
So I didn't get it.
Is it okay for now to suffice that we're not going to put a sign convention on these? We're just going to go with the vectors as you see?
Yeah, it's okay. Yeah.
Okay.
Well, I solved the question in the homework, like look like this one,
Yeah,
and I have to use the negative sign when I solve it. Like one of them should be negative. That's why.
I see.
Yeah, I don't know. That's okay.
Okay. All right. Well, not to leave you hanging, but this whole concept, we're going to come back to this whole concept in like 8 or 10 weeks. And we're going to do what's known as stress transformations and then strain transformations. And when we do those, we will be very rigorous about rotation of coordinate axis and positive and negative. For now, I was trying not to overcomplicate it because I was just trying to show the end result is getting to a stress.
Good. I also solved the problem for 138, and that's what I did. I put y direction going positive and x direction for RV, but making it positive. So I pretty much switched my coordinates. Does that make
Okay.
sense?
Yeah.
So I can get positive for pretty much positive for both of them.
Okay. Okay. Well, I'm not going to be too picky about positive or negative when it comes to the homework problem on this sort of problem. Just looking for the right stress, really. And also remember, okay, maybe I should say this. Maybe I should say this. The normal force, positive or negative on the normal force, has an important meaning that this is in tension. If the arrow was the other direction, it would be in compression. And positive is telling me tension. The other direction is telling me in compression. And that has a very real physical attribute to positive or negative. But for shear, the shear is the same, whether it's positive or negative, depending upon the shear is really just kind of dependent upon what you chose for a reference. If you chose X and Y, or if you chose X and Y going up, would give you a positive or negative shear. Shear is still shear. It doesn't change. It's parallel to the plane. So hopefully this explanation will make you all feel a little better. The shear, we will get to a point where a negative shear or a positive shear, one is right and one is wrong. There is a sign convention that we have to follow, but we haven't got there yet. So for now, it's academic, whether or not the shear is positive or negative. That's why I'm not stressing about it just yet. When we get to drawing shear and moment diagrams, we will define a real sign convention that has to be followed. And then I will start getting nitpicky about positive or negative shear. And as I mentioned, further on down the line, we're going to do stress transformations. And we're going to be very rigorous about rotating the coordinate axes clockwise or counterclockwise. And we'll be rigorous about positive or negative shear at that point as well. But not now, not at this point. So is that satisfactory for everybody, or
Yes. Yes. Thank you.
we're okay? We're okay. All right. Okay. So the point that I was getting to was that I have the force in the shear direction. I have a force in the normal direction. We know that stress is force over area, but what is the area? The area is no longer 2 inches wide by 2 inches high. The area is now 2 inches wide by something else high. This length now is longer than 2 inches. So I need to find what this length is in order to get the full area. And so to do that, I will just use the original, the height is 2 divided by sine of 40 gives me this length is 3.11 inches. So that my area is 3.11 inches by 2 inches wide. I have 6.22 square inches. So therefore my stresses is the 385.7 over 6.22, not 4. So my normal stress is only 57.7 psi. It is positive, so it is tension. My tau shear stress is 459.6 pounds over 6.22 inches squared, or 73.9 psi. and then I box my answer. Okay, so any questions on this type of problem?
I was kind of confused of the slide before with the stresses at the plane.
This slide?
Yeah, the bottom of it.
Okay, and what about it?
Like I just, I don't know. I don't even know what the question. Like I'm just confused about it. I could just go over it again.
Let me try and tell me if something clicks.
Okay.
Okay, so we started with a flat bar that has 600 pounds of tension on it. There's our flat bar. And we have 600 pounds pulling it in both directions, or you're pulling in one direction and you're holding on to it in the other direction. And I guess maybe the point of all this is that if I cut this bar, virtually cut this bar here, and I do a free body diagram, then what I find is that I have a normal stress of 150 PSI. I have 0 shear stress. So far, so good?
Yeah.
Okay. So that's fairly easy to see that a straight up and down produces a normal stress of 150 and 0 shear stress because there's no shear on this bar. Okay, so the point of it though is that there's no reason that I have to draw my cut perpendicular. I can draw my cut at any angle I want. And so if I cut it this way instead of perpendicular, what are the forces that I have on this plane? And in order to get those forces, I have to take my original 600, which is in the horizontal direction, and I need to resolve it into 2 components, a normal component and a shear component. The actual angle of these components is dependent upon the plane that I'm interested in looking at. This plane, this could be 10 degrees, this could be 45 degrees, it could be any degrees. And whatever degrees it is, I can always find my resultants. These are 90 degrees to each other, and the addition of these 2 together will always equal my original 600-pound loading.
Okay. I was just like confused about the bottom part where it's the stresses at the plane, like finding the area of the little section.
Okay, this area here?
Yeah.
All right. So these forces only exist on this plane. If I rotate this plane to something like this, you know, this was 40 degrees. If I rotate this to be like 20 degrees, then these are 2 totally different forces than what you see here. These forces are unique to that 40 degrees. So the more that I rotate this plane, these forces will be constantly changing because they're always based on the degree of the plane. 40 degrees, 20 degrees, whatever the degrees is, dictates these 2 forces. As you rotate this plane, you can see that this length is getting longer as the angle gets flatter. So along a 40-degree plane, the length of this line is 3.11 inches. Along a 20-degree plane, this may be more like 5 inches. If I took a really flat plane, then this length might be 20 inches. It continuously varies. Its minimum is perpendicular, 2 inches, and its limit is almost infinity as this goes to 0 degrees. So what I'm trying to say is that the angle, the forces of your 2 components are dependent upon the angle, but the area of the plane is also dependent upon the angle. And stress is always a force over area. So you have to consider at any angle You have to consider what the two component forces are and what the area that you divide the forces by to get the right stress at any particular angle.
Okay, thank you.
Okay. Now, that does lead to another question I'll ask for you. Basically, the other question is, okay, who cares? Why does that matter? And it's a valid question because as you notice, the original stress from the 600 produced a axial stress of 150 psi. When I rotated it, I went from 150 psi to only 58 psi. So the question could be begged, well, who cares? That's much less than the maximum. The maximum is going to be at a vertical perpendicular cut, and that 150 psi is the most normal stress you can see. Why would I care about any other angle where this is going to be less than 150 psi? And one possible answer to that is to remember that some materials, a lot of materials, are strong in one direction but weak in another direction. For example, concrete. Concrete could be very strong in compression and shear, but it's very weak in tension. Okay, so let me illustrate that. Just take a couple minutes here. This is a block of concrete. And generally, when we load up concrete, we put it in a machine and we compress it like that. And so you would say that at a section of this thing here, maybe just like that, at that section, you would say, well, I've got 100% compression. There's no shear, there's no tension. So what's the problem? That thing's perfectly fine. But at just considering that section, you're ignoring some things that are happening internally in this. So if I was to consider a different section, maybe a section like this, now on this section, I would have a normal force on here that is compression, but I also have a shearing force on here as well. And what actually happens, and again, we'll get to this later in stress transformations, but in one direction, you'll have compression. In the other direction, you'll actually have some tension. And when you fail a concrete cylinder in the testing, it'll actually fail along a line, just like this. That's the failure plane that it fails on. And so why did it fail that way? Because it developed internal tension, and concrete is very weak in tension. So you go out to a testing lab, Twining or Smith-Emery or Kleinfelder or any of those testing labs, you go in the backyard and look at all their crushed up cylinders, and a lot of them will have a shear plane that looks something like that. So it is important, it's an important concept to not just look at the obvious direction, but consider all the other directions that stress is being applied to if the material has a weakness in one direction or the other. Another example of this would be wood. Wood is very strong in tension and compression when you pull or push it with the grain, but if you try to pull it across the grain, it's very weak. And wood is weak in shear when you're with the grain, but it's pretty strong in shear when you're across the grain. It's just the nature of how the material grows in its natural state.
Professor.
Yeah.
You mentioned that we're going to make diagrams or like functions of shear stress and normal stress, like in the future, right?
Yes.
So when we make those, are they going to be functions dependent on the angle in which we cut the material? Is that how they're going to be made? Because the way like I see it is, if that's the case, then we need to make sure if we're like designing something that the maximum load we're putting on a member doesn't exceed the max of, let's say, a shear diagram of all the angles possible in which we cut it. Does that make sense?
Yes, yes, and we are going to get there. We absolutely are going to get there. But what we're going to do is we have to learn how to do finding the stress on things that are more complicated than just something in uniaxial tension. So, and I won't go into this at great length, but say that you have a steel beam, like a wide flange like that, okay? And what we're going to do in the future is we're going to look at just a little element of this beam, like you just went in there with a plasma cutter and just cut out a little segment of that. And then you take that segment, we're going to blow it up. And then what we're going to do is we're going to look at the stresses due to the loading of this beam that might be applied to that little element. So I might have some compression in the horizontal direction, and I might have some shearing on this little guy, like so. And I may or may not have compression or tension in the vertical direction. And so first we have to learn, how do I get this shear stress, and how do I derive this normal stress? We don't have those tools yet. And so we're building up to that. We're going to learn how to do shear and moment diagrams so that we know what the shear is on the whole global structure, and we know what the moment is on the whole global structure. But then we have to learn, okay, now that I have the shear, now that I have the moment, how do I get the stress right there as opposed to up here or down here or anywhere else? It changes. The stress is not constant across the section of this steel beam. So then once we have the tools to derive what the stress is at this particular location, then we can blow it up here. And then what we're going to do is we're going to say, okay, this is the state of stress in the XY direction. But what if I rotate my X and Y by some degrees? What does that do to the stress state? And then we're going to learn how to rotate it through any degree and draw some diagrams that gives us a visual idea of what the stresses, how they are being manipulated as we rotate through different degrees. We're still looking at the same little element in the same beam, but we're trying to get a more global view of it other than just stress in the X and the Y. We're going to look at it stress at any direction. Does that make sense?
Yes, thank you.
Okay. Okay, and I think the last part of this is, just because the stresses may look acceptable on our convenient coordinate systems, and this is just what I was talking about, we like to draw stuff nice and conveniently. So if my beam is going off in the horizontal direction, then I make that my X, and I make the perpendicular Y, and that's very convenient. But just because the stresses may look acceptable on our convenient coordinate systems, there may be other internal angles that reveal a material's weakness. So that's it for now. And well, not that I got lots more to talk about, but that's it for this stress components. Now what we need to learn how to do in the coming weeks, like I said, is learn how to find global forces, then how to find stresses from those forces, and then we're going to revisit this towards the latter part of this semester. Do I have any other questions? Okay. This part, I really like this part of the class. We're going to talk about now stress and strain relationships. We are now forging clearly ahead into mechanics of materials. And the reason why I like this portion of it is that I have done a fair amount of real world testing. where I've done a fair amount of building concrete structures or beams or whatever, and putting them into a jig with a big old cylinder ram and applying loads until things exploded, which is a really fun thing to do. I've also spent a fair amount of time in testing labs where we would test the individual component strengths of those pieces that went into whatever it was I exploded. In other words, rebar, strand, and the concrete itself needs to be tested in a testing lab. And so I've seen this firsthand where you stress something and you get strain. So for every stress of every material, there is a strain. There's always a relationship between strain and stress. And if you're still kind of foggy on the idea, just remember that stress is a force over area. So stress is really just a measure of how much force is on a particular beam or cylinder. Strain is how much it deforms. Strain is a measure of deformation on an inch per inch basis. Okay, so this is what we're getting to. Stress is related to strain by Hooke's law, which states that stress is equal to Young's modulus times strain, or stress is equal to Young's modulus times the average normal strain. That's what this equation is. Pretty simple, but very profound. E equals Young's modulus of elasticity. Young's modulus is experimentally found in the real world, and in your world, it can be found in the tables on the back cover of your text. There's an SI version of the table, and there's a US customary version of the table. And for each one of the materials that they've sampled, you can find Young's modulus. So, Mr. Hooke, I'd like to give, I'm going to start doing this now for this class. I'm going to just give you a brief introduction, very brief, of who these guys were. But Robert Hooke lived from 1635 to 1703. He was an English scientist and an architect. And there he is, as most of the, well, I guess this is just before the Renaissance, but I don't know. Looks like an engineer to me. What do you think? All he needs is a Texas Instruments calculator in his hand, you know, and he's ready to rock and roll. So that was Mr. Hooke. You got a picture what he looked like. And moving on. Hooke's law is only valid in what we will call the elastic region. And I'm going to define that in a moment. But this relationship between stress and strain is only valid in the elastic region. That's very important. Now, since strain is equal to the new length minus the original length divided by the original length, then we can say that delta is equal to the new length minus the original length, where by definition, delta is the change in length of the element, okay? And these are kind of common Greek letter symbols that we use, where sigma is always normal stress, tau is always shear stress, epsilon is always some kind of strain, delta is going to be some kind of deformation. So from this, we can say that the strain, epsilon, is equal to delta over the original length. So the change in length over the original length is also a measure of the strain. Finally, we can say that the change in length, delta, is equal to the average normal strain times the original length. And this is an important way to look at this. Or we can define the new length, L, is equal to strain times the original length plus the original length. Or we can condense that to the new length is the original length times epsilon plus 1. Okay, so when testing a material, we can plot the increasing stress with the increasing strain to create what we call a stress strain diagram. And this is going to be an example of what I call a stress strain diagram. It's pretty customary that we put the stress on the vertical axis and we put the strain on the horizontal axis. Now, once I start testing, and it's really kind of cool now with the modern computerized equipment that we have, you can actually see this live in real time as you're testing some kind of a material. As the machine is pushing or pulling this thing apart, you'll actually see this live in a stress strain diagram. But for now, you just have to imagine that we've started to pull apart some material. And as we pull it apart, it stretches, and the horizontal axis is a measure of that stretch. At the same time that we're pulling this apart, the material is resisting being pulled apart, right? It doesn't want to be pulled apart. So it takes a force to make it move. And that force divided by the element's area is the normal stress. And that's being plotted on the vertical axis. Okay, so everybody clear with this concept?
Yes.
All right. So as we start loading, we can see the stress strain curve progress up as a straight line. This line is following Hooke's law. So that's why this is a straight line. And it's following that the stress is equal to Young's modulus times the strain. This is a linear function. So solving for E, we can see that the slope is the rise over run of the stress strain plot is equal to Young's modulus. So in other words, if I put E over here and I put the stress over here, then the rise is the stress and the run is the strain. So E is equal to stress over strain, which means that the slope of this straight line is E. The slope is Young's modulus. And of course, the more rigid the material is, no, the better term is the more stiff. The stiffer the material is, the higher Young's modulus is, and the higher this slope is going to be, or the more closer to vertical the slope's going to be. If you have a really, what's the opposite of stiff? Soft. If you have a really soft material, in other words, you go from high strength steel to silly putty, something really, really soft. Well, then this is going to flatten out. So it takes very little stress to strain it. And so the line would flatten out. But the point is, in the elastic region, the slope of this elastic portion is Young's modulus. If we continue the loading, it continues up at a straight line. The stress line continues up following Hooke's law in a straight line until, okay, I'm sure you all have already gathered that this will not go forever. Every material has a material limit. And so sooner or later, we're going to hit some kind of material-based limit. And what happens is this thing starts curving and leveling off. So if we continue to load, the stress strain continues up following Hooke's law in a straight line until the material can no longer sustain the induced stress and we hit what is called the proportional limit. And by the way, what I'm showing you in this first example of a stress strain diagram is very much a ductile material. I'll show you what it looks like when it's not a ductile material a little bit later. But all of this that I'm showing you is based off of some ductile material, basically a metal, steel, something like that. Okay, so when we no longer have a straight line, at that moment when it's no longer a straight line, that is the proportional limit. And that's when it starts going in a non-linear fashion. The proportional limit is the end of the elastic range of behavior. So this first portion of the graph here is what we call the elastic region. And from there, from the proportional limit on, we are no longer in the elastic range of behavior. Shortly after hitting the proportional limit, we then will hit the yield stress. And this is what I labeled right there. That's called the yield point. And this is a very important point. The yield stress is a very important engineering property. Most structural design methods will use a material specified yield stress as a capacity parameter. Once a material hits the yield stress, it enters the plastic stage and it will freely yield for some extended amount of strain, like so. So once I hit this yield point, this is really interesting to watch when you're testing the material. Once I hit this yield point, you can physically watch those jaws just continue to move, and yet the load on the material doesn't change. So this is yielding as the strain is increasing. So the length of the sample is getting longer and longer, but the stress is constant. And that's what's known as a yield plateau. And this is very desirable for a lot of things that we build in structures. It is very desirable to have a yield plateau so that if something's really going wrong, it becomes noticeable before it actually collapses, right? This is not collapsing, it's holding the load just fine, but it's deforming, okay? The material will then continue to strain without any increase in stress. The strain that this continues for is dependent on the ductility of the material. However, eventually the material will reach the end of the yield plateau and will start increasing stress again at a strain hardening stage. So now we now enter the next stage. This is called strain hardening. And what is happening is the crystalline structure of the ductile material, the crystals of the steel, get tired of just slipping past each other, and they grab on again. And then it actually takes more load, starts requiring more load, more stress to continue to pull it apart. And this stress will continue to increase until this material hits a maximum or ultimate stress. In this graph here, this is the highest stress achieved in the whole test. So that is the ultimate stress. And after that, the stress will start to decrease. Even though the bar is getting longer and longer, the load it takes to get it to go longer is dropping. It can't even hold the load that it had on it before. So the stress will diminish as the bar continues to get longer until suddenly it will fracture. Okay, Stephen, if you're still with me, I'll keep bringing you back in. Okay, so any questions about this stress strain curve diagram?
Professor?
Yes.
What is the stage before ultimate stress again?
Okay. Let me go like 3 or 4 more slides ahead. I think I'll answer your question perhaps, and then I'll review all the different points. Is that okay?
Yeah, that's cool. Thank you.
Okay. So the whole stress strain curve can be broadly broken into 2 ranges: the elastic range, where the material obeys Hooke's law, and the plastic range where it does not obey Hooke's law. And so here's the elastic range, which is only the straight line portion, and everything else is called the plastic range. Okay, and now let me go back to, yeah, I don't think I have, okay. So if I go back to this point, the very end is the fracture stress. And the fracture stress is just what it sounds like. That is the stress at which point the material separates. Cleanly breaks, it is two pieces, the test is over. The ultimate stress, nothing has broken yet. It's just the point where the material achieved the highest stress possible before it fractured. And if I keep going back, from the yield plateau and all the way over to this is really the strain hardening range. And this flat part is known as the yield plateau. This discrete point right here is where it starts yielding, that's the yield point. And this discrete point right here, where it's no longer going up at a straight line, is the proportional limit. So those are all the different points on this graph. Did that answer your question, Justin?
Yeah, it did. Thank you.
Okay, great. Okay, so there are two very important engineering parameters that we use when we move on past this class into steel design, concrete design, whichever design class you go into. Most of your materials are going to be defined by these parameters. However, I got to remind you that this whole diagram is a ductile material. We will deal with a non-ductile material in a few minutes. So the parameters are the yield stress, F sub y, and the ultimate stress, F sub u. F sub u is here, F sub y is here, like so. So F sub u is, in some material specs, you have to meet a minimum for F sub u. And a lot of material specs, you have to hit a minimum for F sub y. And you'll also define epsilon y, the yielding strain, will also be defined. Generally, these two parameters are defined by the minimum values and with ASTM specifications. Just in case you've never seen ASTM before, that stands for the American Society for Testing and Standards. And they publish zillions of different standards for all kinds of different materials. For example, ASTM A572 grade 50 material, that's a structural steel for buildings, has a minimum F sub y of 50 KSI and a minimum F sub u of 65 KSI. They do not have any minimum for the strain at the ultimate, because that's just way too hard to pin down, but they will define the minimum yield, and they will define how much stress it should carry before it actually fractures. And these are important considerations in designing beams and gussets and columns and things like that. We also have ASTM A706, which is a spec for concrete rebar, the steel that goes into reinforced concrete. And that spec has a minimum yield of 60 KSI and a minimum ultimate stress of 80 KSI. Okay, from Hooke's law, we can find the yielding strain, epsilon y here, as epsilon y is equal to the stress over Young's modulus. For A706, the yielding stress is 60 KSI, and Young's modulus for almost all steels is 29,000 KSI. But you can look that up in the back cover of your book as well for other materials. So 60 KSI over 29,000 KSI is 0.0207 inches per inch of strain, so that you can define where the yielding strain is based on Young's modulus and the yield stress. Do I have any questions on this? Okay. Loading and unloading. If loading and unloading only occurs in the elastic range, then the material will stretch and relax with no permanent deformation. So if you're loading up a material and then you unload it, like picture you have it in the testing machine and you pulled it a little bit and then you let it go again, the stress strain plot will continue to oscillate on this straight line. In other words, there will be no permanent deformation. So if you took a piece of rebar that's 12 inches long and you pulled it, but you did not exceed the yield stress of that rebar, when you let go of it and pull it out of the machine, it will be 12 inches again. There's no permanent deformation. In the elastic range, the material acts elastically. Coincidentally, that's what we call it. The material acts elastically in the elastic range, very much like a spring. So like a spring, you can pull it, you can compress it, you let go of it, it returns to its original shape. If, however, the loading progresses beyond the elastic range, then there will be some permanent deformation. So say I took that same piece of rebar and I pulled it all the way until I got to the yield, and then I kept pulling it and it went through some yielding strain, and then I let go of it, it will rebound along this path, not the original path. This new path will have the same slope, but it's going to have some permanent deformation in it. So in the plastic range, there is permanent deformation. If all the load is removed, there is still a permanent stretch. So if you took all the load back off to zero load, you will end up with something that is stretched out this much because of this yielding mechanism. Any questions on that concept? Okay. Some ductile materials have a well-defined yield point, but others do not. What I'm showing here is a stress strain plot for some high strength steel. Actually, I think it was something like A325 or A490 bolts, which are high strength steel. They are considered ductile. It is a ductile material, but it does not exhibit a well-defined yield plateau. At no point along this curve did it flatten out for a while and then build up again. So why is it ductile? Well, its ductility is in that it has strained so far before it fractured. That's the ductility. But we still have to have some way to define what the yield was if we don't have a well-defined yield plateau. So first of all, the material is ductile as measured by the percent elongation. Percent elongation is the final length minus the original length of your sample divided by the original length times 100%. And this is also in the ASTM specs. Certain materials must have a minimum percent elongation to be acceptable to be used as rebar or structural steel or what have you. So we could also define this as the final strain. So this is where it fractured. This would be the final strain times 100%. So this material here, just kind of eyeballing this to be about 0.19 on the strain. So 0.19 times 100% is a 19% elongation. And that is a measure of its ductility. But compared to the first material, you can see that this material has no clearly defined yield plateau. In materials such as this, the yield plateau is often described by an offset method, where generally speaking, 0.2% is chosen as the offset. So what we do is we draw a parallel line to the elastic line. We draw a parallel line, but we offset by a strain of 0.02. So you can see on this scale, 0.02 is right here. So 0.002 is back here. So we draw that line up parallel to the elastic portion of the graph. And then where that line intersects the graph, we pull a line straight over to the horizontal and read what that stress is. And in this case, this particular material would have a yield, a defined yield of 68 KSI. So where the offset line intersects the stress strain curve, that is the prescribed yield point. And that's how we do it if we can't actually measure a plateau. Go back. So any questions on this? Okay. Brittle materials have a different stress strain shape. Brittle materials might look something more like this. This graph might be representative of a medium strength concrete. Notice that there is no defined yield point. There's no yield plateau, but in addition to that, we don't even bother trying to define some kind of a yield point. There's really no point to it. Brittle materials generally are not defined by the yield, but by the ultimate stress point. In this case, this is 5,000 PSI concrete. So the maximum stress achieved before the concrete exploded was 5,000 PSI. Also notice that the brittle materials do not display very much ductility. In this case, the percent elongation for this material is roughly 0.0032 times 100% or 0.3%. As compared to ductile steel, which was more like on the, generally steel is in the range of 12 to 19%. There's a huge difference between brittle and ductile. Okay, so you want to do some examples? Somebody tell me they want an example.
Yeah.
All right, I got a volunteer, great. So if we have a material with the following idealized stress strain curve, okay, so what does idealized mean? This is just a simple form of the steel that I showed you before. We just kind of smoothed out the edges and we got rid of the strain hardening region for simplicity. And this is something that we will use in design day in and day out, where you have an elastic range and you have a plastic range. So if this is your given stress strain diagram, then we can answer some questions. If the yield F sub y is 60 KSI, as noted right here, if the yield is 60 KSI and the yielding strain is given as 0.0207 inch per inch, then find a value for Young's modulus elasticity E. Okay, so stress is equal to, this is Hooke's law, stress is equal to Young's modulus times the strain. And so rearranging Young's modulus is equal to stress over strain, which is the F sub y over epsilon sub y, which is 60 KSI over 0.0207, gives me 28,986 KSI, or rounded up to 29,000 KSI. Okay, so if I'm given this and I'm given this, basically what I'm given is rise over run. I can find the slope of the elastic region, which is defined as Young's modulus of the elasticity. Example number 2. If the yield is given as 60 and Young's modulus is given as 29,000, at what point does it start yielding? What is the yielding strain? Okay, so I can start with Hooke's law. And epsilon is equal to stress over strain. So the stress is the yielding stress and Young's modulus. So I put in 60 over 29,000 and I get 0.0207 inch per inch is the strain at which we start yielding. And box my answer. Example 3. If the yield stress is 60 KSI and Young's modulus is 29,000 KSI, find the value for stress at a strain of epsilon equal to 0.001 inch per inch. On this graph here, epsilon sub y is drawn right about at 0.02. So 0.001 is right in here someplace. What is the stress at 0.001? Okay, stress is equal to Young's modulus times strain. So I can say that's 29,000 is Young's modulus. The strain is given as 0.001. So the stress is 29 KSI. And we box our answer. Example number 4. If the yielding stress is 60 KSI and Young's modulus is 29,000 KSI, find the value for the stress at a strain of epsilon equal to 0.008. Okay, where on this chart is a strain of 0.008?
At 60.
Past the elastic region.
Correct. It is past the elastic region. It is in this region. It's actually right there. It's in this region. So how do I find the stress at 0.008?
It should be fixed the maximum.
It is. You go up and you see that it is in the yield plateau, and all the stress in the yield plateau is 60 KSI. So there is no equation. You just have to recognize that the strain is in the yielding plateau, therefore the stress is equal to 60 KSI. You can read it from the chart, but you can't use Hooke's law. You can't use Hooke's equation because Hooke's law is only applicable in the elastic region here. And you can clearly see this is the region where Hooke's law is a linear function. This is the region where you're just freely yielding. And so you have to read it from the chart, not from Hooke's law. What would happen if you used Hooke's law? What number would you get? Well, clearly you get the wrong number, but what would that represent? Well, Hooke's law is a proportional limit. So where these two lines intersect, that's what you would get. And you would probably get something like 250 KSI. But that's the wrong answer. This material cannot sustain 250 KSI. It can't sustain more than 60 KSI. So the answer is 60 KSI. And you box your answer. Okay? Any questions?
No, thank you.
All right. If there are no further questions, this concludes today's lecture. This was being recorded, so look for it on YouTube. And we will see you. Have a great weekend, and we'll see you on Tuesday.
Thank you. You too.
Thank you, Professor. Have a good weekend, Professor.
Thank you. You too.